Assalamu alaikum everyone. This is lecture 6 on control system engineering 1. We are discussing chapter 2, modeling in the frequency domain. In the last class we have discussed the how to figure out the transfer function of the translational mechanical system. Today we are going to see how to find out the transfer function of rotational mechanical system, which is article 2.6. And they are actually identical, as you can see in this figure 2.4 for translational mechanical system and figure 2.5 for rotational mechanical system. So the spring is in the both side, then you have damper in both side as well. Only the thing that is changed is mass has been replaced by the inertia. So force has been replaced by torque. The displacement, linear displacement is replaced by angular displacement. So these are the changes that we have. Also now the viscous damper in case of rotational system is represented by D, which was previously been represented by FV. So apart from that, rest of the thing is actually same. Oh, okay, so mass was M. Now we have inertia, that is J, inertia constant. Okay, so let us try to, similar thing applies like the degrees of freedom, how many angular movement possible, linearly independent angular movement possible. So based on that, that many number of differential equations should be there, as well as your free body diagram will also be present initially to understand the topic. But once you are actually familiar with the topic, then you don't have to go into the free body diagram. So the free body diagram will also be a slightly different than the previous one. But don't worry, we'll be discussing in detail most of it. So now let us try to understand one example. I think example it is 2.19. So in example 2.19. So a particular mechanical system, rotational mechanical system is given. So we have something like this. So this is a, now with this rod there is bearing actually holding this device. So two bearing is there, one bearing here in this side and the other bearing is here, and torque has been applied in one side of it. So and this rod is actually can give you torsion or twist. So if you apply torque in one side, whatever the angular displacement in that side, theta t, is not same in the other side. Say in this other side, you have theta 2t. So make it theta 1t, then you have theta 2t. Okay, so torsion is allowed. Torsion is experienced by this rod. So torsion or twist. Okay. So the bearing will give you the friction, D1 here, D2 here, viscous damper. Already torque is there. And since throughout the rod, the twist is not equal, so that is why you can assume that there is two inertia, J1 here, J2 here. And the torsion is actually a spring event. So twist, it is actually applicable in the spring. So that is why if you try to find out the corresponding diagram, schematic diagram in the mechanical domain, then we'll have something like this. So we just take one reference, then because of the D1 or the friction one, then you have one inertia here. Okay, then you have, because of the torsion, you will have a spring effect. So spring is there, then you have another inertia. Then the second inertia has been held by the other bearing, so D2. Then you will have another reference, mechanical reference. Okay, so this is the schematic diagram from the physical diagram in the mechanical domain. So this is your D1, this is your J1, this is your J2, this is your K, and this is your D2. Okay, so torque has been applied here. So torque T in the time domain. But I actually prefer the tau symbol than the T symbol for the torque. So let me write in that way. But if you want, you can follow the book's T notation. So then you have theta. So theta 1T. And in the other side of the spring, you will have theta 2T. So theta 2T. So actually, the angular displacement, separate angular displacement is possible because of the spring and the friction effect, but it is not possible for the inertia. So basically, writing theta 1 here is same as writing theta 1 here, same thing, theta 1t. So you can do that. Okay, so in the both side of the inertia, the theta is not getting changed. So similarly, also you can also write theta 2 here, theta 2t. Okay, so this is what is allowed. Now, let us try to figure out the corresponding transfer function of this one. So again, as we already said, that you have to use a free body diagram for this one. Okay, so, but this will be also a circular free body diagram. So now how many degree of freedom is there? There is 2 degrees of freedom because of the fact that there is 2 separate angular displacement possible. So because of the movement of J1, maybe because of the movement of J2. So now you have to apply the superposition theorem, or in case of mechanical, the free body diagram. So so say that J2 is stationary, and J1 is rotating. So on that case, say this is your J1. And on J1, the rotation, the torque is being applied in this direction, say tau T. And always we assume, like in the previous case, that the linear displacement is in the same direction as the force. So we also try to assume similar thing here. So theta 1 T will be in the same direction. Actually, if you want, you can also write in terms of directly in terms of the Laplace parameter instead of writing the time domain, because we already are familiar with it. So we can do that here as well. So directly we can write in Laplace domain. So say theta 1s, and this is your tau s. Okay, so and also now because of this, whatever the other torques produce, there is 2 types of torques. One is torque, applied torque, and other is consumed torque, or generated torque or consumed torque. So the consumed torque is always in opposition to the applied torque. So basically, whatever the torque that will be produced, so because of its own inertia, because of this friction, and because of this common one, so there is 3 opposing force, opposing torque you're going to get. So this will be J1 s square theta 1s because of the movement of theta 1. Then you will have the other one in the opposite direction will be because of the damping, that is d1s theta 1s. Then as well as your because of the spring effect, because if J1 is trying to rotate in the clockwise direction, the spring because of its opposite force, it will try to force in the opposite direction. So it will be k theta 1, k theta 1. Okay, so this is because of the self movement. So what is the condition? Condition is J1 is moving, J1 is moving and J2 is stationary or standstill. Similarly, now we are assuming that J2 is rotating, J2 is rotating, and J1 is stationary or standstill. Okay, so what will happen to J1 in that case? So for J1, now you will only have one force. Okay, so this is also, J2 is also trying to rotate in the clockwise direction. So because of this clockwise nature, the spring will have a anti-clockwise force on it. But since J1 is stationary, it will be equal in opposite direction. So it will also have a clockwise rotation. So you will have on J1, it will experience a force because of the rotation of J2 in theta 2. So you're going to have something like this, K theta 2s. Now, if you combine these two, and then what you are going to get is on a single body, you will have 3 in the torque, and this one will be added together, and that has to be subtracted from the other 3 because we have summation of all the forces. So on J1, superposition we are now trying to apply. So, so this is your tau s. This is your theta 1s. Then you have the opposing forces, J1 s squared theta 1s. Then you have D1 s theta 1s as well as K theta 1s. And the other one that is additive, that is you can give maybe this direction here, that is K2 theta 2s. So bottom line, these two are having same direction and the other 3 in the opposite direction. So actually we could have easily avoided the free body diagram, but it is always better to know fundamentals so that in someday if you have to derive it from the basics so that it doesn't become that difficult for you. So what we are going to get here is J1 s square. We can directly take common of the theta 1 s. So D1 s plus K theta 1 s equal to tau s plus K theta 2s. So now we can easily take all the thetas in the one side. So J1 s square plus D1 s plus K theta 1 s minus K theta 2 s equal to your tau s. So does it seems familiar to you? Just like in the previous mechanical or even in the electrical domain, what we see is the summation of the impedances. So these are the impedances in the for the rotational mechanical system. So as you can see, the impedances are shown here. So summation of the impedances with the angular rotation, and then common impedance, which is K in this case, in between theta 1 and theta 2. We have K in between, so common impedance into the rotation of the other side, other loop maybe. Okay, so equal to your torque. So this is your equation 1. So how can we find out the equation 2? For the equation 2, so what is the common? So we are not going to the free body diagram again for the rotational mechanical system. Rather, we are directly writing the equations. So K theta 1s. This is for the movement of theta 1. What is the experience, the force experience, the torque experience on your J2. So plus self impedances, all the self associated impedances, that is Z2 S square plus, then you have D2S plus K is common, so theta 2S equal to, there is no torque on it. So this is your two differential equation required to represent the rotational mechanical system, which is almost similar to your translational mechanical system. And also now you can apply the Kramer's rule. So if somebody asks you to find out what is the transfer function g of s, which is given as theta 2s by your ts, in that case, what you have to do, you have to find out what is your theta 2s, and that from the Kramer's rule, easiest one. So from the Kramer's rule, you can easily find out. So you have J1 s squared plus D1s plus K. Then you have minus K theta. Sorry, minus K. Then you have tau s and 0. And then you have del. So now you can easily find out. So it will be just tau s times K by del equal to your theta 2s. So basically your g of s is equal to theta 2s by tau s equal to K by del. So del just the determinant of the coefficients of theta 1 and theta 2. So you can easily, I think, can figure out how to do it. Okay, so not that complicated. It is rather just based on the previous idea. It's just a, so, but you have to have some basic knowledge of the mechanical system. So, but don't worry, we know that we are in the electrical domain. So, we'll time to time, we'll try to go back to mechanical systems. More and more practice can make things easier to deal with. Okay, so maybe you can also take help of your mechanical friends, so they can actually help you to figure out how to find the schematic diagram. Then from the schematic diagram, from the physical system to the schematic diagram, then from the schematic diagram, rest of the thing actually you can do it by yourself. It is always a cooperative or collaborative work, so you have to think in that way. Now let us try to solve few more problems. So say example 2.20. Now here another system is given. So this is the reference. Then you have a damper. Then you have inertia. Then you have spring. Then another inertia. Okay, then another damper. Then you have another inertia. Finally, using the damper to your reference. So basically, this is your J1. This is D1, then K, J2, then you have D2, then J3, then you have D3. Now, how many rotation is possible here? We already said that in case of the inertia, it doesn't make any difference. So you give theta 1 maybe here, theta 1t. So because here also it is theta 1c, so it doesn't make any difference. But outside other side of the spring, there may be a different theta angular displacement, so that is theta 2t. Similar thing is also applicable, so theta 2 can also be appearing here. But the damper and the spring, actually in the both side of it, there may be a different angular displacement possible. So you'll have theta 3 here, theta 3. So theta 3 also can be here. Then the other side is just the reference. So now if we try to write the equation, so we don't prefer to go for the free body diagram, rather we'll go for the summation of the impedance, then the common impedance and the rotation of the next one, then the common impedance and the rotation of the next one. So this is the linking that we want to try to establish so that we can easily implement the idea. So now let us try with the equation. So before that, we should also know, is there any torque or not? So actually the system has a torque here. Torque has been applied here. So or same as applying here. So torque is T is here. So let us try to write the equation in the Laplace domain. So for the first angular movement, so what we are going to get is J1 s square plus you have d1 here, so d1s plus the spring is coming as well, so this is your theta 1s. Then what is common in between angular movement 1 and 2 is the spring k, so minus k theta 2s. So is there any common in between theta 1 and theta 3? No. So in that case, it will be simply 0 theta 3, 0 theta 3s, or just simply 0. And also the torque is being applied here, so tau s. So this is your equation 1. So for the equation 2, what is common in between 1 and 2 is basically the k. So minus k theta 1s. Then the whole impedance of the two angular rotation or 2. So basically what we are going to get is J2 as a square plus, then you have D2s, 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 then you have K. So this is your theta 2s, and theta 2 and 3 is related by the damper theta 2, so minus d2s theta 3s, but there is no torque, so basically you can write 0 here. So next is your, for third one, there is no linking between 1 and 2, so you can get this minus 0, 0, something like this, and then you have this, then common in between 2 and 3 is d2s minus d2s theta 2s, then all the impedances of the third one. So basically J3 s square plus 2ds you have, so d2 plus d3 s, but there is no spring effect, so theta 3s equal to 0. Now you have three equations, three unknown to solve, theta 1, theta 2, theta 3. So you can easily find out the corresponding transfer function that is been that you are being asked to figure out. Okay, so next is a skill assessment exercise 2.9. So skill assessment exercise 2.9. Skill assessment exercise 2.9. What it says is you have to find out the transfer function g of s equal to theta 2s by ts. Okay, so now look at the system. So the system gives something like this. We have an inertia here. Then we have a spring. then we have a damper, then those goes to location where from which actually there is another spring going to surface, okay, and there is another damper that goes to surface as well. So one question you may ask whether these two references are the same or not. So okay, so it may or may not be, because some friction can be with some other surface than the spring effect that has been related to. Okay, so now, but according to the schematic, they can be joined together, even though physically they may be separate location, in the separate location. Now look at here. So what we have is all the magnitudes here, like J1 is given in terms of the real parameter 1 kg meter square. Then the spring constant is given 1 Newton meter per radian. This one is also given 1 Newton meter second per radian. So Newton meter second per radian. And also all of them are actually having quantity 1. So now how many rotations should be there? First of all, there should be definitely, because of in these two sides of the spring or damper, there should be two different rotations. So even though they haven't given it, or what they have given is just the torque here, T, as well as they have given one rotation here, that is theta 2T. Okay, so we know that there is in the two sides of the spring there is different rotation. So we can assume that there is a rotation here that is theta 1 T, as well as sometimes it may seems confused, but because you have written two different equations for two different inertia, so it may seem difficult for you to comprehend what is happening. In that case, actually you can assume that there is a inertia as well here, okay, but the magnitude of which is J2 equal to 0. So then maybe it will be easier for you to understand what is happening. Okay, so let's try to solve this one. You have to find out the transfer function in between the angular displacement 2 with respect to the torque that is applied actually into angular displacement 1. So how to write it? Let's say that the two equation definitely should be there. One for theta 1, for theta 2. So let us write the equation, the first one. So J1 S square plus common is D1 SA. This is your D1. This is your D2. And this is your K2. This is your K1. Okay, so D1S plus K, then you have theta 1S, then common in between them is D1 plus D1S plus K1, theta 2S equal to your torque, applied torque. Okay, so if you go for the magnitude, actually what we are going to get is S square plus S plus 1, because all of the quantities are 1. So S square plus S plus 1 theta 1S minus S plus 1 theta 2S equal to your tau S. Similarly, we can write the equation for the second one, second angular rotation. So basically this common is same, so minus S plus 1 theta 1S. Then all the impedance of the second one. So J2 is 0, so we can easily omit that. So basically what is left is D1, D2, K1, and K2. So 2s square because of the d1 d2, so 2s square plus 2 theta 2s. There is no force applied on it, so this is 0. So now based on this two equation we have to find out theta 2. So theta 2s is basically s square plus s plus 1, then minus s plus 1, then we have tau s by 0 divided by s square plus s plus 1 minus s plus 1 minus s plus 1, then you have plus 2s plus 2. Okay, so the numerator what you're going to get is basically tau times tau s times s plus 1. In the denominator, if you just cross multiply, then you can take common of 2 here. So 2 s plus 1 s square plus s plus 1 minus s plus 1 whole square. Okay, so in the denominator you can take common of the s plus 1. So s plus 1, if you take common, what you are going to get is 2s square plus 2s plus 2s square plus 2s plus 2 minus s minus 1. Okay, so tau s plus 1. So s plus 1 getting cancelled out. So now what is left is theta 2s by tau s equal to basically 1 by 2s square plus s plus 1. So this is your required transfer function. Okay, so things are not that complicated, but definitely not in the things are not from the electrical domain. So that is why you may need to practice more to get more familiar and to get acquainted with the system. But as I already said, that actually you can take help of your friends. Okay, so next thing that we are going to see is basically Article 2.7. Article 2.7. Let's see, where is the figure? So this is the figure. So Article 2.7, and it will start with the gears. So transfer function, let me write here. So Article 2.7, transfer function for systems with gear. So transfer function for systems with gear. Okay, so this is your Article 2.7, and gears are being shown here. Basically, gears is similar to the electrical counterpart, that is transformer. So transformer. So what is the function of the transformer? Transformer, actually we know that using the transformer, what we can do is number one, we can change the voltage current level. So voltage current level. Okay, so voltage current level. Number two, what you can do is there is a 180-degree phase shift. 180-degree phase shift in the transformer. We can do impedance matching or impedance shifting. So impedance matching. Okay. Then also we can go for if you have a system with different with a transformer, then what do you have to do? You have to bring them to the same level, okay? So same voltage level before actually calculating or doing some analysis. So same voltage level, same voltage current level, voltage current level. Okay, so similar thing actually applies for your gear system, mechanical gear system. The first question, why you need transformer? Because somehow the voltage or the current that we are getting is not enough, or in some cases in the generator side to step up the voltage, then step down the voltage. So similar thing also may happen in a mechanical system. The load that is the motor that you have and the load torque that is required, they may not match. So in that case, changing the entire motor is difficult. So rather than that, to match the torque, we can use the gear in the middle. So gear can step up or step down the torque as per requirement of the load torque. Similarly, correspondingly inversely, basically the theta or uh, angular rotation will be also inversely up and down. So if torque is increasing, then theta will be decreasing. If the torque is decreasing, then the theta will be increasing. Just like the voltage and the current. If the voltage increases, the current decreases. Or if the voltage decreases, then the current increases. So this is similar. So in a gear system, what is happening? The torque and the displacement. Torque and the speed or the displacement, whatever you like. Displacement, angular displacement. Okay, so this is what has been changing. Next thing that is happening is also there is a 180 degree fixed phase shift, as you can look here. So the theta one that or applied torque, because of that you have a direction of the rotation in the clockwise direction here, but in the other shaft, other gear, what is happening is counterclockwise. So exactly 180 degree rotation. So reverse rotation is also there. Reverse rotation. Okay, same. Impedance matching, we'll derive it and you'll see that the transformer that whatever we apply, that ZL prime reflected impedance in the primary side is A square ZL. So here this is actual impedance, actual load impedance, which is referred to the primary side with the turns ratio square. So similar thing is also applicable here. Here we call it teeth ratio. So teeth ratio square can actually help you to take the impedances from one side to the another side. And also, if you want to find out the differential equation with the transformer, or you want to do some analysis with the transformer, then you have to bring it to one side, either everything to the primary side or everything to the secondary side. So same thing also goes for your mechanical system. You have to either take everything to the source side or everything to the destination side. Okay, so this is how actually you have to go for it. So as I already said, that mechanical gear system are actually almost identical in every nature to our transformer in the electrical domain. So let us try to derive the corresponding formula for the gears, mechanical gear system. So first thing is by default, it is already known. So if the radius of the smaller one is R1, the radius of the bigger one is R2, and which is directly proportional to the number of the teeth. So this is your number of teeth. So this is by convention. So teeth is proportional to your radius. This is how it is actually designed, number of teeth. Similarly, for this one as well, so number of radius will be proportional to number of teeth. So we can easily write one formula R1 by R2 can be written as N1 by N2. So this is one thing. Number two, the contact space or the arc of these two gear is same. So arc length S1, which is for the smaller one, has to be equal to same for the other one, that is S2. So say this arc length, which is equal distance for R1 and R2. So we know that arc length is proportional to R1 into theta 1 equal to R2 equal to theta 2. Okay, so from this one, we can easily find out the relation between R and theta. So basically, we can say that theta 2 by theta 1 can be written as R1 by R2. Okay, so which further can be related with your turns ratio. So N1 by N2. So bottom line is, what we can conclude here from this ratio is basically theta 2 by theta 1 is N1 by N2. Okay, so theta is similar to, I should say, current in the electrical domain if you consider transformer. So transformer. Now, what is the relation between the torque and your teeth ratio? So let us look at that one. So we know in transformer, one assumption that we always take that input energy is equal to the output energy, same as electrical. Same as electrical, we can also assume the similar thing in the mechanical. So energy as supplied and the energy dissipated should be equal to, it should be equal, so they should be same. Ideal case, just for deriving the formula. So similarly, energy in the mechanical system, energy 1 or supplied should be equal to energy dissipated. So basically, this is tau 1, theta 1 is energy supplied, and energy dissipated is tau 2, theta 2. So from this one, we can easily find out the relation. So that is basically theta tau 1 by tau 2 by tau 1 can be written as theta 1 by theta 2. Again, theta 1 is inversely proportional to theta 2, n2. So basically, you can write n2 by n1. So one relationship is this, and based on this relationship, what we can say that if you have a system with gears and you want to find out what is the output displacement theta 2, then your transfer function has to be something like this, n1 by n2. If you give theta 1 here, then you're going to get theta 2. Similarly, using this one, what we can say that output torque tau 2 can be related with n2 by n1. So basically, if you are interested to find out what is tau 2 from tau 1, then it will be n2 by n1. Okay, so these are the two corresponding transfer function for your how the torques or the displacements are related. Now, one thing is left is the impedance matching part or impedance transformation part. So how we can actually look at that one. So for that one, say we assume that already we have solved similar things. So we already have seen this part with the inertia. One thing you have to remember that gear is only applicable for your rotational mechanical system. So that is also you have to keep in mind. It is by most of the time it is common sense, but still, since we are not from the electrical domain, it's better to mention that we are not from the mechanical domain. So now this is the scenario. Already we have solved in the last article how to find out the corresponding transfer function. So it is nothing new. So now let's just add the gears. So these are the symbol for gear. So you have gear here connected. So this is your N1 teeth of the smaller gear, maybe then teeth of the bigger gear. Then you have torque being applied here, tau 1 t. Then you have theta 1 t. I think it would be better if you can erase this portion. Okay, so next is there will be a reverse direction in the other side of the gear. So you will have a reverse direction. So if this is clockwise, then the other one will be anti-clockwise direction. And say this is your theta 2t, theta 2t. Now you have to find out the formula for impedance matching. We already said it will be teeth ratio square, but let us try to do that, how to deal with it. So this is your J, this is your D, this is your K. So now there is two options. So just to make it similar to the electrical, so we just say this is your primary side, maybe primary side. This is your secondary side. So just like in the transformer, you have the flexibility. You can go either to the primary side or to the secondary side. Okay, so say we are just writing the equation. So one thing we haven't write, but we can always assume that if there is a torque theta angular displacement in the other side, there should also be a torque here, so which is tau 2 t. So it will not be a difficult thing for us to write the equation for the secondary side. So what will be the equation for that? So JS square plus DS plus K. Okay, so that will be related to your theta 2 S should be equal to your tau 2S. Okay, so similar idea. Now, actually, we want to transfer all these impedances, this one, this one, this one, to the other side. So that means we have to find out the relation in terms of tau 1 and theta 1. So just replace those by the equation that we have derived, by the transfer function that we have figured out here. So theta 2 is basically theta 1 times n1 by n2. So just write that thing here. So n1 by n2 theta 1 s. And similarly, the tau 2 can also be written as n2 by n1. So n2 by n1 tau 1s. Okay, so js square plus ds plus k. Now you can take all the teeth ratio in the same side, so take it in that side. So what it will be becoming is n1 by n2 whole square. Then you have js square plus ds plus k equal to theta 1s, and then you have tau 1s. Okay, so we can insert this inside the bracket. So what we are going to get is j times n1 by n2 whole square, s square, don't forget s square, plus d n1 by n2 whole square s plus k n1 by n2 whole square. So then you have theta 1s equal to tau 1s. Okay, so this one can be called reflected impedance to the primary side. Okay, so you can write J equivalent plus B equivalent, oh, don't forget about S, S plus K equivalent theta 1s equal to tau 1s. Okay, so basically the same idea that we have applied in the transformer, turns ratio square was the factor that was bringing us the parameters from one side to the another side, either turns ratio or 1 by turns ratio. But in the mechanical domain, to make it, to keep it simple, you can also write something like this: number of teeth of gear on destination shaft, on destination shaft, divided by number of teeth on of gear on a source shaft. Okay, so this should be the square. So wherever you go, so either to the primary or the secondary, so the destination shaft will be the determining factor. What is mean by that? Say you want to go to primary side, so impedance will be mapped by destination is N1. Okay, so N1 by N2 whole square, then you can bring everything here, every impedance in that side. But if you intend to go other way around, like from the primary to the secondary side, in that case, if there is an impedance, how that will be related? So destination is now N2, so N2 by N1 square. So with whatever the corresponding J given, so that will be J or D or K, so that will be related in that way. So let us try with one example, then the idea will be even more clear to you. So let us go for one example. Example 2.1. Example 2.21. So one mechanical system is given. Okay, so then you have a gear here, then you have another one. Okay, so another inertia, J2. Then you have the springs, then you have the reference. So basically, just like the mechanical, just like the electrical transformer, you have to remember one thing is that the transformer, what happens? The components that we have here in the other side. So once we remove the transformer using the turns ratio, this point is becoming actually single point. So similarly, if we can eliminate this one, so this is actually a continuation also, same point. So that is why this is what you have to keep in mind. So that is why you can actually make a summation of these components. Okay, so now these two, say just in series, J1 and J2, so they can be added together. And like this one is with respect to this point to the ground, so this one is also with respect to this point to the ground. So if you can just add those two, those the friction coefficients can also be added. So initially it will be slightly difficult to understand at the beginning at times. So even now I sometimes get confused here about it because of the fact that we are not from the mechanical domain. So it's natural. So you don't have to worry about it too much. Rather, you try to practice more and more. As I said, practice can actually make things familiar, and then it will be a lot easier. So this is the system that has been given. Now you have two choices: either take everything to primary side or take everything to the secondary side. Even though the terminology may not be correct, rather they're actually shaft side. So which shaft side you want to go? But for us, it is easier to recall. That is why we are just calling something similar like that, going with the primary or secondary. So now, bottom thing is that if you convert it, then you'll have a system like this. The inertias group together, as well as your friction group together. maybe. So with respect to the reference, so this is your equivalent diagram. So this is your J equivalent. If you are, it depends on you whether you're going to the primary side or the secondary side. So D equivalent and your K equivalent. So K equivalent will simply be K2. It is also given 2 because it is in the other side. This is your D2. This is your D1. So what will be your J equivalent? Writing the J equivalent, say we're taking everything to the secondary side. So secondary side means destination is N2. So J2, J equivalent will be, J2 is already there. So J2 plus J1. J1 is shifting to the secondary side, N2 by N1 square. Let's see. What is D equivalent? D equivalent is D2 is already there plus D1 into N2 by N1 square, N2 by N1 square. Similarly, you have K equivalent, which is K2 only because we are already in the secondary side. Okay, so this is how you have to find out the model. And then also if since you have taken everything to the secondary side, so your torque is actually applied in the primary side. So we actually have to find out the torque tau 2t as well as theta 2t. Theta 2t. Okay, so theta 2 we don't have to worry about too much. So if you can write the equation, what will be the equation? The equation will be J equivalent SS square plus D equivalent S plus K equivalent, which is already figured out what are the parameters. So into theta 2S, which is the one that we need already in the on that side, equal to tau 2. Tau 2S. But the relation has to be in terms of tau 1. Or okay, so tau 2 can be replaced by N2 by N1 into tau 1S. So this is the only change. Then you have the rest of the thing becoming here exactly. So G of S, which is G2S by tau 1S will be actually N2 by N1 divided by your J S square, J equivalent S square plus D equivalent S plus K equivalent. So what is added in addition because of the gear, what is happening? This parameter is added. This parameter is added, which is will actually it's just a multiplying factor is been added with your transfer function. Okay, so this is how you have to do it. Let us do two more example. One is so example 2.2. Example 2.22. So in the example 2.2, we have a diagram like this. Okay, so torque has been applied here. Tau 1 t, then you have theta 1 t. So turns ratio, teeth ratio is given N1, N2. This is your N3, N4. Okay, so inertia given, so J4 given, J5 given. Here in this side you have J3. Here you have D2 and J2. And the primary side you have J1 and D1. So what they want to find out is the equivalent diagram of this one. And then what is theta 1s by tau 1s. This is your G of S. And this is what you have to figure out. So everything, it will be better to take if you can take everything to the primary side because the ratio between the torque and the angular displacement and the torque is something that you have to figure out. So now one thing you have to be careful that this J1 and J1 and D1 is in the primary set already, so we don't have to use any multiplying factor with that one. But D2, J2, J3, they're in the middle, and J5 and J5 and J4 is another level, another tooth ratio apart. So basically now, if you want to find out equivalent diagram, the diagram will be looking simply like this. You will have an inertia component. This other side of the inertia component is open, so we keep it as it is, and you have the friction. Friction is always with respect to some surface. Okay. Sometimes air friction can also be there, but still we can assume that there is a surface. Okay, so this has to be your D equivalent, this has to be your J equivalent, then you have your torque T1T as well as your theta 1. Okay, so now what will be J equivalent? So your J equivalent will be equal to J4 and J5. They have to go two transformation. One transformation N1 and N3, and another transformation N1 and N2. So you can write directly something like this. First of all, J1 is already there, so we keep it J1 there. Then the next level you have J2 and J3, which will go with one transformation. So destination is N1. So N1 by N2 squared with J2 plus J3, and J4 and J5 will need two transformation. So first of all, it will go to the second level, then it will be going to the first level. Okay, so it will be N1 by N2 and then N3 by N4. Destination divided by the source teeth whole square, that will give you with the multiplication of J4 and J5. So this is your J equivalent. Similarly, D equivalent you have to figure out. So in the third level, there is no D here. So only in the second level you have one, and in the first level. First level will be as it is. So D1 plus in the second level to the first level, it will be N1 by N2 whole square into D2. So finding out the equivalent transfer function is a matter of just a simple calculation now. J equivalent S square plus D equivalent S into theta S or theta 1S equal to your tau 1S. So theta 1S by tau 1S is simply 1 by J equivalent S square plus D equivalent S. Okay, so as you see, things are not that complicated, whether they are just a matter of practice, how much practice you put into. Accordingly, it will become more and more easier. Now, finally, one skill assessment exercise with some numerical value. How can you do that? Let us do skill assessment exercise 2.10. So this one will, you have a simple network, one mechanical system that is one inertia with a damping, then you have gear, then you have a spring, okay, then you have the reference. So all the parameter again one, you have given torque here, torque here. So as you know, how many rotation there should be, as I already said that just like transformer, this is the same point. So you just shift it from one side to the another side, that's it. So, but there should be one angular displacement theta 1 here. There should be another one here or here, same thing. Okay, so basically that will be your theta 2 will be coming here. Theta 2, yes. Okay, so now let us try to find out the equivalent diagram of it. So what you have to find out is g of s equal to theta 2s by tau s. So it is better to take everything to the secondary side. Okay, theta 2 is already there. So what will be our equivalent diagram? Our equivalent diagram will be very, very simple. So basically, this is what we are going to get, inertia. Then you have this, you have, and then you will have a spring as well. Okay, so friction, and then you have this. Okay, so what will be your J? J is going to the other side. So J equivalent will be, you have to find out J equivalent. Then you have to find out the D equivalent. Then you have to find out the K is already there. Okay, K equivalent also maybe. So this is given 1, this is given as a 1, this is given as a 4, and the ratio is also given as a teeth ratio 25 and 50. So we are moving to the secondary side. So what will be our J equivalent? Our this is your actually it's better to give the opposite direction. So this is your tau 2 t and theta 2 t. Theta 2 t. Okay, so let us find out the equivalence first. So J equivalent will be equal to J is going to the secondary side, so secondary tooth, that is 50 divided by 25, and the magnitude is 1, so actually 2 square, that is 4. And similarly, D equivalent will be also 50 by 25 whole square with magnitude 1, so it is also 4. So if now you write the equation, then what we will have 4s square, because J equivalent is 4, plus 4s plus k equivalent is k is which is also 4. Then we have theta 2s equal to tau 2s. But our relation says that we have to figure out in terms of tau 1. So you just replace the value here. Tau 1 is basically n2 by n1, n2 by n1, tau 1s. Okay, so 4s square plus 4s plus 4, theta 2s. So what we are going to get, n2 by n1 is basically 50 by 25, so it will give you 2. So theta 2s by tau 1s will be 2 by, you can take 4 common, 4 s square plus s plus 1. So basically 1 by half s square plus s plus 1. So this is your required transfer function g of s. So this is your mechanical, rotational mechanical system basically with gears, how to deal with them. So there are a lot of exercise problems at the end of the book. I always prefer you to go with those, make it more familiar so that it becomes easy for you to approximate their corresponding schematic diagram or block diagram. So in the next class, we'll be actually discussing article 2.8, that is electromechanical system transfer function. So that will be our next topic, that article 2.8. Okay, let me stop here in this class, and maybe inshallah we'll see you in the next class.